How do, folks? Welcome back to the second day of relativity here in 4C. So what we're going to do today is talk a little bit more about space-time diagrams. We're going to do a couple of examples. We're going to look at some of the weirdness, and fun and games will ensue following that. Just as a reminder, remember your PLC, which is the traffic light, is due Friday, so please just make sure to submit that. It's an easy one to let go now the celebration's over. But just check it off, send it in, and you'll be good to go. And homework 7 is posted and is ready to get going. I have the due date of 5/1 for that, which is next Thursday. So we'll see how we go, and we'll go from there. Regardless, there will be a quiz as usual that same day, and we'll go from there. So day 2 on relativity. So at this point, on some of those homework problems, I'm seeing that you should be able to complete probably, and there's a 9 total of those. So you should be able to do, I think you should be able to do about half of them already just based off yesterday. Okay, let's go ahead and keep going with special relativity and space-time diagrams. We left off with the space-time diagram of the street lamps, and I think we were just about getting finished with talking about what ordering things were in. So moving on from that, what we have today is to talk a little bit about what happens when we do try to change frames and what are the consequences of these perspective shifts. So it was a pretty big day yesterday. So let me go back and just review a couple of the high points that we hit involving the consequences. Well, not consequences so much, but more like the setup of how we're considering relativity. So the first big thing to come away from that class with is that the speed of light is invariant. All right, which means that it's the same for all observers, and you could add the word inertial in there, so all inertial observers, because special relativity ultimately is an inertial set of ideas. It's it's essentially in some way replacing what Newton's first law is doing for us. Or maybe I should say it's extending what Newton's first law is doing for us. Okay, so instead of just saying objects continue to move at a constant speed in the same direction unless acted upon by a net force, we're saying, okay, well, let's take a look at the mechanics of what happens when we have a speed of light which is an invariant to different observers, and we're all moving at whatever speed and we're continuing constant velocities, right? Constant speed in a straight line. How do things look when we jump between frames? So the first one is that speed of light is an invariant. And I'd like to talk about that as a consequence of some of Einstein's postulates for special relativity, and that was one of them. I mentioned on this yesterday, I mentioned this in the previous class, that Einstein's postulate, when he started thinking about what does it mean to be in relative motion at constant velocity with respect to someone else. How do you tell, right? And if you have no external reference points, okay? In other words, you cannot see things going past. There's no obvious signposts, or there's no landscape changes. There's nothing you can see. Suppose you're in a closet with no windows. Okay, and the only thing you can do is do little experiments in there. You drop things and throw things, and you're trying to look at the trajectories of these objects in order to see, well, are they changing? Are they the same as what I would expect if I was at rest on Earth's surface? And so you find that they are exactly, the results of the experiments you do are exactly as if you were stationary on Earth's surface, as long as you're moving at constant speed in a straight line. You can't tell the difference between these two situations. There's no experiment you can do. Excuse me. And so that was essentially Einstein's postulate, which is that the laws of physics are unchanged to any inertial observer. And therefore, are unchanged to any inertial observer. Oh, remember, we got one other thing here today, the lab 10, or is it lab 10 or 11? Lab 10 is due today. That's the other thing I forgot. This is Thursday. That's right, gave you a little extra time. So lab 10 due today. Okay. All right, back to this. Laws of physics are unchanged to any inertial observer. Right, inertial, taking the Newton first law idea, inertial, constant velocity. Okay. One in which the law of inertia holds. The law of inertia is one in which when you put something down, it stays there. When you push something, you experience it moving away at a constant speed, right? At a constant increase in distance, right? So this is essentially the word inertial is synonymous with constant velocity. All right. Now, Einstein goes in to thinking about, okay, what happens to perspectives? What happens to measurements? What happens to the observers as they change frames and then they come back and compare what their measurements are, right? And he starts with this, but I want to kind of think about the idea of light speed being an invariant is actually a consequence of this, okay? Because, just like I was saying, if you're in a dark closet and you're throwing things or dropping things to see if their trajectories are changed, so you can do the same thing with light. What if I had a light beam on one side of the closet and a detector on the other side of the closet, and I shot the light beam this way? And I detect it over here, and I say, I know my closet is this big because it's just a closet, and it should take light some amount of time to get from one side to the other. If I were able to detect a difference in that time because of the motion of my closet with respect to Earth, right? So say that there's suppose that there's a laser beam, and suppose I'm in motion in my closet with some speed relative to Earth. If I shoot the laser beam this way, does it also pick up a little speed? Then I have it reflect and come back, and it shoots back this way, and I detect a difference in the speed of light. Can I detect a difference in the speed of light? I have to be able to say that every measurement I do should come out exactly as if I were stationary on Earth. That means light has to take the same time back and forth in my closet just as it would on Earth if I were stationary. So if I had the ability to detect changes in the speed of light based on my motion, that would violate the idea that the laws of physics are unchanged for inertial observers. And that would be really distasteful, because that means now we have to come up with different laws of physics for you and you and you and you, because you're all moving at different speeds. So you're telling me as soon as you start walking, the laws of physics are different for you? I hope not, because that means we now have a lot to deal with, right? The ideas of the laws of physics are that we kind of adopt a reductionist viewpoint to these things, right? We try to take a few things and apply them to large amounts, not have specific things for every single situation, like a biologist or a chemist, right? Oh, if it's this way, it's got to be one of those. But if it's doing this, oh, it's got to be this thing. And if it's this, oh, it's this other thing. That's too much to remember, okay? We only have limited space. And so we want to take only a few ideas and have them be widely applicable, okay? That's the idea of physics laws, right? So that's a consequence of this idea here, okay? Okay. So light speed, not just a constant anymore, it's an invariant. It's something that is the same for all observers. All right, so we'll start with that. And we'll go with speed of light. Okay, so what else did we talk about last time? Not only that, but we talked about the idea that space and time are being measured in human quantities. We have units for space, distance, and time intervals, which do not match and are really there because they're convenient for us. But from a physics standpoint, what's the difference? These are just dimensions. Okay, these are just dimensions. I've got a space dimension and a time dimension. What's the difference between those two? Well, there isn't really a difference, so we should be able to measure them in the same units, and therefore we can change the speed of light to something that's a little bit more tasteful rather than being some big, huge number that no one can remember. Well, you probably all remember it, but it's big and cumbersome and hard to work with, so we also change units such that c is equal to 1. And it is technically unitless because it's a meter per meter. What I'm going to do is I'm going to go ahead and say I'm measuring time in meters. So how do we do that? Well, if you think about what the speed of light is in SI units, it's a meter per second. What that's telling us, since that's the same number for everybody, that's telling us how to convert a second into a meter, right? It's or things with time units into things with distance units. So technically this is unitless, but I'll say it's a meter per meter. In other words, it's a meter of how far the thing is traveling per meter of light travel time. Therefore, you end up measuring all speeds relative to 1, because light travels 1 meter per meter of light travel. That's what light does. It's just like saying how many years would it take light to travel from a star which is 4 light years away? Well, the unit is constructed such that you know exactly what the amount of time is. The distance is 4 light years. Therefore, the time is 4 years. So in some sense, you've already been indoctrinated to this. This is a meter of your travel time divided by a meter of light travel time. And it's a meter, and it's a meter, so the meters go away. So c is equal to 1. Was another thing. And then we talked about the space-time diagrams and how to interpret those. So we'll go through a few more of those today, but before we do that, what I want to do is go through and look at some consequences of the speed of light being invariant. So let's do that. And we'll start off by, as we will in a couple of examples today, examining what happens on a train. So here we are, we're on a train, and we have what is possibly the simplest clock that we can come up with, right? Clocks are pretty complicated. You have all these gears and turning things and electricity sometimes, or mechanical pendula or something like that. Let's just do something really super simple that everybody should agree on. And it's a clock that's made of light. So I have a light emitter and a light detector, and I shoot light from the emitter, say a laser or something, or whatever it is. I shoot the light, it hits a mirror and comes back. And when it hits the detector goes ding. All right, so I just registered one time unit of whatever this is. So all I got to do is sit there and click this laser beam on and off at a regular time interval, and the detector will go bing, 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 right? And it'll give me a way to keep time. So here we are on a train, and what we've done is we've installed in the middle of the train, let's see, where's the middle of this train? Looks like it's about here. So in the middle of this train, we've installed a light emitter, which I'll just put with a large arrow here. So this is the emitter. And next to it is a detector. All right, and on this side, light emitter. Okay. Now, in order for the light detector to be able to detect the light, I've got to be able to have it bounce off something at the top of the train here, so I'm going to put a mirror up here. And I'm going to assume that either the light is going slightly at an angle up and down, but it's essentially negligible in terms of the distance that it's going, or the light detector and emitter are basically right on top of each other, so it goes straight up and comes straight down, okay? That means the path of the light as it goes up would follow right, one of these, and I'm gonna just do this so it comes down and it hits the detector there. Right, it's going up on that side and down on this side. Therefore, the light is taking a path which traverses, and I'll also assume that these are relatively thin so that there's not much of a difference in the light's distance and the height of this train. I'm just going to call it light's traveling as the height of the train. The light travels up the height of the train and down the height of the train, so its path of travel is twice the height of the train. Okay, so maybe the train's like, I don't know, 3 meters tall or something, such that we're interested in how often is the, or say, what's the time it takes between clicks of the clock, right? So let's say that every time this light detector registers a pulse of light, it tells the emitter, okay, emit again, right? The emitter goes and releases the light, goes up, comes down. The detector goes, got it, okay, go again, right? So it goes again. So that the time between, kind of, if you like to think of it as ticks of the clock, which is the light getting detected by the light detector, is equal to the time travel that the light takes to go up and down the height of the train twice. So the time between clock ticks which I'll just say in quotes there, is going to be, which I'll just call delta t, and I'll call it delta t, say, I was going to say emission and detection, but that would mean delta t ed, and I don't want to write ed, so let's just leave it as train. I'm going to put a big line here and I'm going to put train, so that we know that that's evaluating the time interval as if I were standing on the train watching this thing, okay? And the time must be 2h divided by c, because light's traveling at c and it went a distance of h up and h down, okay? All right, so no problem. Seems relatively straightforward, hopefully. let's change things up a little bit. Because trains move on rails and go past stations that are on Earth, suppose that when we go past a station, I'm going to imagine that we're going to draw the same situation from the perspective of someone who is not on the train. Because what we've done here is implicitly assumed, and I kind of mentioned it a little bit, that we're standing right here. And I'm looking at the emission and the detection, and I'm watching the detector, and it's going up and it's going down. So I'm drawing this from the perspective of someone who is on the train, not moving with respect to the clock. Now what I want to do is imagine that I've been pushed off the train, and I'm standing on the platform at the station, and I'm watching this train go by. The train's not going to stop for me. It's an express train, right? So it's going to be moving past me at constant speed, and I want to ask, what do I see as the consequence of this light emission and detection scheme here, all right? So down here, I'm going to try and draw what it looks like from the perspective of someone on the platform. All right, now I'll have to draw a couple of frames because I want to do it at successive time increments. So let's suppose that I do, let's see, how far over can I go here? Start about here. Let's suppose that I can do a train car, and I want to do it, how many do I want to do? There's 2, 4, 6, 8. All right, so I'm going to draw all the same stuff as I had before. My detector's right here. All right, so here at time, say this is at time t1, as measured on the platform, this is the first thing I see as the train is coming by. It's just about to start an emission. Okay, so the light is just about to come out of the laser. And as it does that, the train is moving past me, okay? So the next thing I see as my clock is ticking and I'm watching this, I should also put that this train is moving with some speed like that. Okay, I got this thing being 2, 4, 6, 8. Okay, I'm going to draw the same thing again. Here's the mirror. Here's the emitter. Here's the detector next to it. Okay, and this is at time t2. And it's still moving with speed v. And then at time t3 later, it's over here. 2, 4, 6, 8. Like so, all right? So I've got 3, this is at time t3, moving with speed v. Okay, so hopefully this makes sense what I'm drawing. I've just drawn the same exact train car at 3 different points of time as I'm standing on the platform watching it go by at some speed v. And now at t1, I notice that the light has been emitted. So my question is, what is the path that the light takes as observed by someone out here on the platform looking at it this way? Okay. So you might ask yourself the question of something, for the example, if we stand here, okay, and I look at this situation up here with the train, and I just toss something straight up, it lands right back in my hand. Well, okay, no, let's try that a little. Okay, so it lands right in my hand, or it doesn't. just exactly as the light goes up and down here. Now, suppose that I'm in motion relative to you, and you're seeing me moving past, but the same thing is happening. This is still happening to me, right? So I'm just doing this. I'm gonna get a nice repeatable, see if I can get a nice repeatable toss so that it never leaves the plane of my hand. It never leaves being above my hand. So what happens if I'm in constant motion now with respect to you? Now it looks like this. What's the trajectory now of the object? Okay, right? You probably saw it's exactly what you'd think it would be. We don't have quite that because I've got a very sharp turnaround point here. So it's almost as if you can't quite see, but if I threw it up and it hit the ceiling, if I threw it up really hard and it hits the ceiling and bounces off, it wouldn't be curved the way that perhaps you saw it on the screen, but it would go up and then hit and reflect and come back. So that's the trajectory that we're looking at when the light is emitted by the emitter and the train moves past. And then subsequently is detected by the detector. So light is emitted from here and hits the mirror like that, and then comes back down and hits the detector here like that. Oops, there we go. Like so, all right? Therefore, the path of light that we see, that one's a little bit darker than this one. I'll try and darken this in a bit. The path of light that we see when we are out here on the platform is one in which the light travels this distance. Say it's a distance little d or something like that. Distance is little d. The height of the train car is still 3 meters, say, right? And it's still h. So if I take a look at the triangle that's formed by the light travel, just this half of it right here, then I think you'd agree that this path that the light takes from here to here is much longer than just a single height up, right? Or if you like, the reason I'm doing half of it is because this entire travel length looks like much greater than up down, okay? The light has literally gone on a longer path. And therefore I would ask, from my perspective out here on the platform, what is the time between emission and detection of the light? What's this delta t as seen by someone on Earth, say, or on the platform? It should be 2d divided by c, where d is the hypotenuse of this triangle, right here, okay? Remember, light is still traveling at c. So just because I've gone from being on the train to being out on the platform, light still travels at the same speed. Light travels at light speed for all observers, and that was inertial and this is inertial. So we see light traveling at the same speed. But you'd agree that I'm looking at light traveling a longer distance, and therefore light must be taking a longer time because it travels at the same speed. Therefore, this must be a larger number than delta t Earth. Not delta t Earth, delta t train. Delta t Earth would be a larger number than delta t train. Okay, so what does this mean? Carefully thinking, what have I said this delta t is? It's the time between what and what. There are 2 events happening, and you know already, everyone agrees on an event. There's no disagreement on events. It happens. So light getting emitted here, that's an event. Light getting detected there, that's an event. Light bouncing off the mirror, that's also an event. okay? So we're gonna take these events and we're gonna say, we must agree these events happen, and the time between the events is given by this delta t. In other words, it's like the time between ticks on the clock. It's almost as if you just kind of, you blow this up a little bit and say, hey, maybe that's like 1 second. Okay, obviously it's not 1 second because this is a small train and light's traveling really fast. But imagine that it's something like ticks on a clock, okay? So the time between ticks is different, which means the amount of time elapsed is different. Okay? So I think you can see that if I'm talking about the time between ticks, then the amount of time as seen on the train by an Earth observer or a platform observer, the amount of time on the train as seen by an Earth observer is less. Why is it less? It says greater. Because the time between the ticks is longer, which means it undergoes fewer ticks for a given amount of time. So if I say, for example, I want to look at my watch while the train goes by, and I notice my watch goes tick, 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 tick. Then I'm going to notice the train's clock going tick, 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 tick. It's a slower rate of time moving, okay? Therefore, because it's a larger amount of time between the emission and the detection, it's a longer time between the ticks, and therefore less time elapses on the train, according to someone on the platform. Time between ticks. So this means train time. Okay, notice that this is a comparison between the train times. This is not a comparison between train time and platform time. This is a comparison between train times. Train time from the platform viewpoint. Am I still on here? Yeah. You see that? Yeah. From platform. Oops. Okay, so this is my conclusion here. This says that the train time from the platform is slower than the train time from the train. Does it make sense how I kind of reason to this? Okay, light travels a longer distance. Light travels the same speed for all observers. Therefore, if it travels a longer distance, it takes a longer time to do that. Therefore, the amount of time between clicks as seen from a platform is longer than as seen on the train. Therefore, there's less time as seen from a platform observer on the train than by a train observer. In other words, if I observe a clock that is moving, then I observe its time to be slower. What do I mean by slower? I mean slower than, for example, my watch, okay? Or if you like, it would be slower than if I was on that train and I was looking at the watch. It would be ticking what I would say in a normal sense. But now I'm watching the clock go past and I'm seeing it's not ticking at a normal rate, it's ticking at a slower rate. And therefore, time is moving slower as I observe it when the clock moves past. Okay? No problem, right? Makes total sense. This gives rise to a very common catchphrase that we have here in physics, which is the idea that moving clocks run slow. And this is bad English. Because it should be run slowly. Anyways, the idea, moving clocks run slowly. But you'll get laughed at if you say that. Not in the English department you won't. They'll say, good job. All the physicist people will go, moving clocks run slow. Everybody knows that. It's not slowly. All right, so let's take a look here at a way to mathematically represent this. So what I'm interested in is the times, all right? So suppose that I looked at the times, I said, okay, if I say that h is something like 3 meters, okay? I'm gonna just visually draw this out for you. Delta t on the train is gonna be equal to 3 meters. Suppose the height of the train is 3 meters up and down. That's a tall train. Okay, fine. 3 meters up plus 3 meters down, right? That's 2h. Got to divide by c, but guess what? C is equal to 1. Isn't that great? This is why you love c being 1. So it's 3 plus 3 divided by 1. I've got that one. 6 meters. Right? That's equal to 6 meters. Yes, 6 meters. That is a delta t. 6 meters. Yes. 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 Okay, now let's take a look at what is it as observed by a platform person. Delta t as observed from Earth. The Earth observer viewpoint tells us it's 2h divided by c. In this case, let's suppose that it's a 5 meter, the big long line that goes up and down is a 5 meter distance. So it'll be traveling 5 meters that way plus 5 meters that way. That's also going to be divided by c, which is 1. And you'll note that at this point, I'm going to get a larger number, which is what we expected. It's 10 meters, which tells us, yes, the time between ticks is larger because it took light a longer time to go from emission to detection here than it did here. It traveled a longer distance from here than it did here. So clocks that move relative to another observer. Okay, let's make sure that we're careful with this. We observe their clocks running slow. Okay? If you get on the rocket ship or train or whatever it is, and then you look at the clock, you will not observe the clock running slow because the clock is not in motion relative to you. It's only when you look at clocks that are in motion relative to you that this becomes applicable, okay? Which means that if I watch a train or whatever go past and I look at its clock and I look at my clock, I say, oh, the train clock is running slower. Now, if I jump on the train and I look at my clock, this clock's not running slower. But if I watch the clock on the platform go back the other way, I'd say, that clock's running slow because it's in motion relative to me. All right. So there's a nice symmetry here that gives rise to a fun paradox, which we'll hopefully talk about today, but maybe if not, we'll talk about it next Tuesday. Okay. This path being longer, this time being longer, is a result of the train moving. Okay? Let's represent this by saying that delta t on the train, if I take that and I square it, I'm going to notice something here. If I notice there's a 6, 10, and I had a triangle here, so I would know that if I thought about a 6, 8, 10 triangle, then that would be something I would know something about. I know something about triangles, and you do too. We have the 3, 4, 5, we have the 6, 8, 10, we have the whatever, everything else, right? So suppose that I squared the 6, and I said the 6 is a consequence of the time it took the clock to tick, and also the distance the clock moved relative to me as that tick was taking place. So let's suppose that this is equal to the time on Earth squared, like this, minus something else. Because right, look, this is the 6 squared, this is 10 squared. Okay? Well, I know that in order to make that work out right, I've got to do a minus 8 over here, squared. Because it's a 6, 8, 10 triangle. So that would mean that if I did a 6 squared over here plus an 8 squared over here, that should give me the 10 squared over here. But I don't have that. I've got 6 squared over here, which means I got to go 10 squared here minus 8 squared over here. But that 8 squared, what is that? The 8 squared turns out to be the distance that the train must have traveled in that time. Okay? That turns out to be delta x as observed from Earth squared. Right? So that this turns out to be 6 squared equal to 10 squared minus 8 squared. And indeed, this should work out because this is 100, that's 64, and 6 squared is 36. So it mathematically works out, but this also gives us insight into how do we deal with times and distances like this, okay? What we do is we do the difference in the squares of the times and the distances. So this is just an example, and I'm going to take this one example and make it a general thing. But what I want to notice is this is a slightly different geometry than what we're used to, okay? In other words, we are thinking of times and distances, and we're taking we're squaring them, and then we're taking their difference, okay? You might think, well, wait a minute, that's not true because if I look at a space-time diagram, then I would look at something that looks like this, x and t, and I would see an event that happens right there. And I would say, look, that event has an x and a t to it, okay? That event has an x and a t, but what you're saying is, oops, I missed. Try it again. What you're saying is, this distance, say s, delta s, the distance from the origin to that event point isn't the Pythagorean theorem. Because it sure looks like it should be, right? That's a point, that's the vector that goes from the origin to the point, to those coordinates, and therefore shouldn't that make a triangle in which this is a hypotenuse and these are the two legs? No. That's not what we're drawing here. You just can't see it. What we're drawing here is a completely different geometry, and it's not easy to see. Mostly because I haven't showed it to you. But the geometry is more along the lines of subtracting these two things rather than adding them. So if you're aware of the conic section geometry, this is a hyperbolic situation here. Okay? This is what gives you hyperbolas. So the geometry that we're dealing with is not Euclidean. This is not a Pythagorean theorem where you're going to go, oh, that x squared plus t squared equals t squared. No, it's minus. Okay? So this is a non-Euclidean geometry, and we're not going to explore a whole bunch more than that, but I will say it's really interesting, and I encourage, if you're enjoying pursuing this type of craziness, go take the next step in something like this, like a 4D class, and we'll talk about the hyperbolic geometry. All right. So it's not Euclidean. We have non-Euclidean geometry, and therefore what we would say is that the distance between events is actually given by the square of the time minus the square of the space between them. I'll put distance in quotes because this is really a space-time distance. It's t squared minus x squared. Or delta t squared minus delta x squared, however you like, okay? But one thing you've got to be really aware of is these two things have to be occurring in the same frame. Notice it's delta t Earth minus delta x Earth, okay? All right, let's just go off this here for a minute. If I say that delta t of the train is equal to delta t of the Earth, oops, sorry, I forgot the squareds. Squared. And I think about the distance that the train traveled in that amount of time, as seen by an Earth observer, would it not be true that the distance the train traveled in time as seen by an Earth observer should be just the velocity of the train multiplied by the difference in the time? The distance the train traveled between the emission and the detection, that's a time interval, and the train was moving at a certain speed, so shouldn't the distance just be equal to speed times time? Yeah, it should. This should just be equal to v times delta t Earth. Okay, so if I say, oh, well, this is equal to v times delta t Earth, then all I got to do is put in v times delta t Earth over here. And then I can factor it out. I'm going to have that squared. And then I'm going to factor this out, and I'm going to notice something interesting happens. All right, this is delta t Earth. And I'm going to factor out the squared, and I'm going to end up with 1 minus v squared here. Now, if I divide in the sense that I'm going to take the train time as something that I know, because maybe I'm on the train, and I look at the Earth time as something I'm interested in getting. In other words, I know what my watch is reading, and I want to know what that watch is reading, okay? So if I do it that way, then I'm going to swing this 1 minus v squared underneath over here. I'm going to say I'm going to solve for what the delta t on the Earth is going to be if I know what delta t on the train is going to be. All right? If I do that, then what happens is I get this, delta t Earth is equal to delta t train, like that, divided by 1 minus v squared. And remember now, v is a number that cannot be greater than 1. In fact, it shouldn't be equal to 1, because if it was, that means the train's traveling at light speed. And therefore, there are not going to be any time, clicks between the time emission and detection, because the train's going to be traveling as fast as the light is. So the train's never going to, or I should say the light is never going to catch up to the train detector. This quantity, 1 minus v squared, is so important we call it something. We define it as gamma, which is 1 divided by, oops, I forgot a square here. I forgot squares. This has a square root on it now because I just dropped the squares off there, so I square rooted the whole thing. Great, square root of 1 minus v squared. That's what gamma is right there. We define gamma to be basically a time stretch factor. It's related to how much different is the time going to be on that clock versus the time that's on my clock. And it's given by this thing, which pops up again and again and again. And we'll see it's going to pop up real soon again, just as we get to lengths. All right. Okay. This is basically the time stretch factor. Even though it's also responsible for other things, we've discovered it in the context of time stretching, so we'll call it the time stretch factor. It's also sometimes called the Lorentz factor. Okay, so let's take a look at an example. Let's suppose that you are living in the 24th century, and you want to go take a rocket ship, you want to take a spaceship trip to some planet way over there. And so you're going to walk over to your local rent a rocket place and you're going to go, hey, I want to rent a Starship and I'm going to fly over there. And you go, okay, no problem. Here you go. And you go, wonderful. I'm just going to rent it for a week. I'm just going to be gone and I'll be back. So we grab the spaceship, you put down your deposit, off you go. All right, you're looking at your watch, it's ticking along merrily. You go, oh, yeah, I've been on here a couple of days. A couple of days longer, I'll be there. You get to the place you're going, and you look at your clock and you go, okay, I've spent a week getting here, right? I spent 1 week getting here. When you land on the other planet, which is way over there, they go, oh, no. That's 3 weeks you've been gone. You took 3 weeks to make that trip, not one. And you say, no, wait a minute. I don't need to pay for 3 weeks. My clock says 1 week. Question, how fast were we going? And so, a 1 week trip. So we'll say a 1 week trip results in 3 weeks of getting charged. In a 3 weeks charge. So first question, how fast were we going? Okay. Okay, before we get to answering that with math, let's look at it on a space-time diagram. Okay, here's T and X, and this is from the Earth frame. We'll assume that we rented our rocket here on Earth, and we're blasting off and going to some place that's a week away by rocket, which would be like, I don't know, are we still in the solar system at that point? I would say probably not. We're going somewhere that's a hitherto undiscovered planet, which is close by. So here we go. Our light line, okay, the C line, I'm just going to dot that in here, goes right here. I know that my prime axes have to be symmetric about that. That's one of the things we talked about yesterday. So my time axis of my rocket ship is going to look something like this. I'll call that T prime. Actually, I'm going to incline that a little bit more, I think, just so you can see it a little bit better. My time axis is going to go like this, T prime. Let's put it over there. Therefore, my X prime axis is going to be likewise like this. All right, but I'm getting to a place where the other planet is located, and let's just suppose it's over here. All right, here's the other planet. So I left Earth here, and I'm going to, I don't know, just for convenience sake, let's make up a name. I'm going to, oh, for goodness sakes, I'll just call it Pluto. I know it's not Pluto, but we're going to the other planet. I'm going to call it P for planet Pluto. All right, here's my T prime axis, which is my journey. It's like what's called a world line. It represents my journey from E to P. All right. Now, notice, I'm going from here to here, and this is where your Euclidean geometry is going to fail you, right? Your Euclidean geometry thinking is going to fail you. You're going to go look at this. You're going to say, oh, it's this point right here where the rocket landed on planet P. And according to the t-axis, that time is 3 weeks. But according to my time, it's only 1 week. So the time has different space between the hash marks, right? You'd say, okay, here I've got a 1, I've I've got a 2, and it's a 3. So there's 1, there's 2, and there's 3. But on mine, I'm going to have 1 is up here. 1 is right there. So the first thing to notice about this is not only are the axes inclined, but the hash marks, what do you call that when it's the spacing between the 1, 2, and 3? It's different on the prime axis than it is on the unprime axis. Okay? So yes, it's weird because the time here is less. This is what you would consider the hypotenuse of your triangle in Euclidean thinking, right? This hypotenuse is a lower number than this leg because it's not Euclidean. So you can't think hypotenuse and Pythagorean. You can't think that because that's not what's going on. So yes, the hypotenuse is less than the leg. All right. What we're going to do is we're going to use this to figure something out. All right. So here I'm just going to calculate this. Now we got to make analogies between, okay, who's the train and who's Earth? Okay. Well, not surprisingly, Earth is Earth and the train is the rocket ship. So that delta T Earth divided by delta T train is equal to gamma, the time stretch factor. And that we know is equal to 3. So all I have to do is now go back into gamma and solve for what V is. If I do that, that means I've got to square everything, flip it over, subtract it from 1, and then square root the whole thing. So that means I'm going to get V equal to, I got to square it, flip it over, subtract it from 1, and then square root it. Okay, it should look like that. 1 minus 1 over gamma squared. Square root of that. Okay? In this case, gamma is going to be 3, so this is going to be 1 minus a ninth. I'm going to flip that over and square root it. Is that right? 1 minus, maybe I shouldn't have flipped it over twice. I should have not flipped it over twice. I think it's this, 1 minus 1 over gamma squared. If I square that, flip it over, subtract it from 1, and then square root it. Yeah, it should be that. So if you calculate this number, it's going to be a number like 0.9 for a gamma of 3. It's something like 0.95 or 0.94 or something like that. Let's say 0.94. So we're cooking, which is pretty good. I want to introduce a little bit of terminology, okay? The time on the clock that didn't move. Which clock didn't move? You'd say, well, it's got to be Earth clock, right? Well, no, because Earth clock is now way over there, right? I was on Earth, and now I'm on planet P. So if I look at Earth clock is like way back there now. So it moved a long way. I can't be talking about planet P time because it started way over there and now I'm on it. So planet P clock must have moved too. What's the clock that didn't move? It's the one I'm looking at all the time right here. If I'm on the rocket ship, it's my clock. The clock that didn't move is the clock on the rocket ship. Wait, what? We all know the rocket flew from there to there. No, it didn't. No, it did not. I got on the rocket and I looked at my watch, and then all of a sudden I looked up and I was at planet P. I didn't go anywhere. That clock stayed right there the entire time. So what Earth did was Earth suddenly up and took off that way, and planet P came over this way, and I landed on it and I was like, oh wow, my clock is still right here. This clock never moved. I watched the Earth clock go that way, I watched planet P clock come this way, but my clock never moved. So the time on the clock that doesn't move, train, I said train, but train/rocket, is known as the proper time. In this case, the proper time is that one. It doesn't move. Doesn't move. What do you mean doesn't move? Relative to the observer. Blah, blah, blah. Relative to the observer. Okay, let's take a look at another example. Let's suppose now that, let's just make things a little bit easier. So let's suppose this is 0.95 instead of 0.94. Or we could keep it at 0.94. Maybe that does make it easier. Okay, never mind. We'll keep it at 0.94. And what we'll do is we're going to now do this example again. And what we're going to do is we're going to say, okay, I'm going to start at Earth. I'm going to fly off to this planet. I'm going to hang out for a little while, and I'm going to fly back to Earth. What do I see? So the first part of that space-time diagram, we've already got that drawn. Okay, my example now is I fly out. Maybe I'll make this a different planet. It's one that's a little further away. Suppose it's like really far away. Suppose it's say 80 light years away. No, let's suppose it's 40 light years away, so it takes 80 light years there and back, all right? So now we're going to go on a trip, a round trip, should say round trip, to a planet that's 40 light years away. Okay, so a large part of this first part of relativity is trying to figure out which clock is telling you this, okay? Note that in this expression up here, I have 2 times. As you're getting used to doing these types of things and looking at what's happening with what and who's going where and which clock is moving here, you're going to try and assess which clock is which one has the proper time, which one's the not, which one's the improper time, which one's doing this, which one's moving there. And so it's a game of trying to recognize what clock is telling you what. And it'll be a little bit challenging at first. So just to let you know, you might try this a couple of times and you'll get the proper time on the wrong one. But that's okay, because we're here to help you. So round trip to a planet that's 40 light years away. Who has the proper time? Is the question here. In other words, which clock is not moving? Well, the answer is the same. It's the one that is on the rocket, is again the proper time in this case. Round trip to a planet 40 light years away. How much time elapses on the rocket? All right, how much time elapsed on the rocket? Slightly different question, but same basic idea as over here. I need to know delta t on Earth. I need to know delta T on the rocket. Oops, I should put gamma this way. Gamma times delta T on the rocket. Or on the train, or whatever you like, all right? Now in this case, we know this number. This is the time on Earth. 40 light years away. Oh no, sorry, not 40 light years away. My bad. To a planet. 40 years, not 40 light years. Sorry about that. Just erase the word light. It takes the rocket 40 years to get there. Okay. As observed by an Earth observer. Okay. So in other words, what I'm saying is that this 40 years is that number right there. Because that's the amount of time that we have aged watching that rocket go from here to way over there. Okay. Now, if it's traveling at 0.94 and its gamma is still 3, then all I have to do is figure out, okay, what's delta T rocket? Well, it's delta T Earth divided by gamma, which means it's 40 divided by 3, and that's about 16.7 years. Okay. Is that right? That doesn't seem right. 32, what's 40 divided by 3? It should be 13 years. 13.3 years. Okay, what does this mean? This means that as we on Earth watch the rocket go from Earth to this planet, and we say, man, I'm 40 years older than I was when that rocket left. The person on the rocket says, no, I'm only 13 years older, 13 and a bit older than I was when I left. The times are different because the flow of time is different when you are in relative motion to one another. So what's going to happen? The rocket's then going to turn around and come back. And it's going to turn around and it's going to be gone for 26.6 years. Whereas on Earth, we will have aged 80 years. Okay? And so when the rocket gets back, the person on the rocket ship is only 26 years older, but we here on Earth are 80 years older. Yes, this happens. This happens. You got to travel kind of fast to notice it, but yeah, this happens. All right, so here is our trip. Here's the T prime axis there. This is the trip out to the planet, right there. And here's the planet P, and here's Earth over here. All right, so same basic idea as last time. So the question is, how much time has passed on Earth? Well, this is the really interesting part. This is the interesting part, which means that, remember I said that if I was on the rocket ship watching Earth go that way, I would have said, well, Earth clocks are in relative motion with respect to me, and therefore their clocks are running slow. But the people on Earth are going to look at my clock as I go zoom away on the rocket ship, and they're going to say, well, look at that rocket ship time, it's running slow. So each of us is going to see the other's time as running slower. How do we resolve this? Okay, we're going to do it by simultaneity. So the rocket leaves, and we both say 0 on our clocks. The rocket leaves and arrives just as it's about to arrive at this planet P. I look at what's on my watch as I am on the rocket, and it says 13.3 years. So on the T prime axis right here, that's 13.3 years. Okay? On Earth, we would go straight across to read the Earth time. That would be 40 years, right there. Remember, these tick marks are at different spacings. But what does it look like if I'm on the rocket ship and I turn around and look at Earth's clock? If I turn around and look at Earth's clock, that's a simultaneous event that happens right when I arrive at the planet. So simultaneous with me arriving at the planet, I turn around and I look at Earth's clock. What does Earth's clock read? Earth's clock reads, and I have to go, where's my 45-degree line is somewhere like there, which means my x prime axis is somewhere like there. So I'm just going to go like this, about like there. Which means that I observe Earth's clock as being this amount of time. Now, that means that it's going to be 13.3 divided by 3, because to me on the rocket ship, Earth moved away at 0.94. So that means I'm watching their clock run at a gamma of 3, slower than my clock. Well, my clock read 13.3, so their clock has to read something like 4.7 or something like that. What's that divided by 3? 13 divided by 3. Who knows? Whatever it is. Let's say it's about 4.7 years. So clearly my diagram is not quite right. This should be way down here. Okay, fine, I'll do it that way. It's more like down here. Simultaneous. There it is right there, 4.7 years, right? In other words, that's 13.3 divided by 3. That's what I, on the rocket ship, see as Earth time simultaneous to me arriving at the planet. Now what happens is I, on the rocket ship, stop, turn around, and go back to Earth, which means I reapproach Earth going like this. And I look, and just as I leave the planet, I go, I wonder what the time is on Earth. And what you'd find is this is going to be 80 years as seen on Earth. And what this is going to be is 85.3. No, yeah, it's 85.3. No, it's 75.3. 75.3 years. So from my perspective on the rocket ship, this is how I traveled forward in the future. It's a really funny kind of thing. You can travel forward into the future by going really fast and then stopping and turning around and going back. Because when you stopped and turned around, look what happened to Earth's time. Remember, simultaneous with me stopping and looking back at Earth, and as I arrive at the planet, I see Earth's clock. They went that way, according to me, at a really high speed, and their clock is running 3 times slower than mine. So their clock reads 4.7. Okay? When I start my journey then back to Earth, I look at their clock again, and I go, wow, their clock now reads 75. Because for me, I'm going to watch Earth coming straight at me at a gamma factor of 3, and therefore it's only going to take 4.7 years by Earth time for me to get there, by Earth time as I observe Earth time. Okay? So that means that when I stop, turn around, Earth's time swings wildly from here to there when I stopped and turned around and went back. And therefore, by doing that, I'm jumping into the future of Earth. And I'm only going to age 13.3 times 2, 26 point some odd years. And they are going to have aged 80 years. And this is a real effect. You could have said, any clock would have told you that. And that means any clock, like your pulse, time literally slows down for moving clocks. Your pulse is going slower. The brain signals are moving slower. You don't notice it though, because you're just like, yeah, man, everything's cool. But if you're watching it in a clock going past, you're looking at everything in that time, everything to do with time in that frame is slower as seen by you. Not as seen by them, but as seen by you. All right, well, we only got to this much, so I guess I talk a lot. That means next week we'll start with another situation on a train, and we'll go from there. But in the meantime, start taking a look at some of the space-time diagrams on the homework, and don't forget to submit your PLC and your lab today, PLC tomorrow, and then I'll have another lab getting posted up for you tomorrow. Alrighty, so with that, I will say happy rest of your day, happy good weekend, and start being specially relativistic. Alrighty, see you later.